Hey guys, Mr. Bowman here. Today's learning objective is in yellow, and we are learning to use our integration skills to solve problems in kinematics. And key thing, what I've underlined is really important. I have underlined integration because we're now learning how to apply our integration skills as opposed to our differentiation skills. And we've got a question from our book on the bottom left, and we're going to be using this as our starting point. So let's get into the question. The acceleration, so key thing there, acceleration of a meteor in the Earth's atmosphere is given by the acceleration with time is equal to 1 plus 0.2 times time, where t is the time in seconds since the meteor has entered the atmosphere. Question A is asked us about the meteor takes 45 seconds to hit the Earth. What is the acceleration as it hits the Earth? So what that's saying is it's 45 seconds after going into the Earth's atmosphere is when we're interested in. So we know at that point there that t is equal to 45. And this question is actually a simple substitution. We're going to go the acceleration at 45 is going to be equal to 1 plus 0.2 times the t. So we're going to get rid of the t and we're going to substitute in the time that we're interested in. And that there is going to be equal to 1 plus 9, which will be equal to 10. And our units would be meters per second squared. Okay, question B. The velocity of the meteor when it first enters the atmosphere is 4,000 meters per second. Find its velocity function. So if you recall our little table, so we've got the displacement in terms of time, then we get the velocity in terms of time, and then we get the acceleration in terms of time. And to go backwards, you actually need to integrate. So our starting point would be the velocity in terms of time would be equal to the integral of the acceleration. And that's going to be the integral of 1 plus 0.2 t dt, which is going to be equal to t. And don't forget that t there has a power of 1 plus 0.2 divided by 1 plus 1 times t to the power of 1 plus 1 plus c. And that there is going to be t plus 0.2 over 2. So that's 1/10 of t squared plus c. So that is our integral or our velocity equation. The only thing is we've got the plus c, so that's not a completed equation. So we need to figure out how to calculate that. And this is what makes the integration questions a bit harder because you need to know about a bit of other information. And in our case, they've told us about the 4,000 meters per second. And they've also used the word when it first entered the atmosphere. So what that means, when t is equal to 0, when it initially enters the atmosphere, the velocity, so the velocity of 0 is going to be equal to 4,000. And we can use that information to finish our equation. So we know 4,000 is going to be equal to 0. Noticing I'm getting rid of t and substituting in 0. Plus 1/10 of 0 squared plus c. All of this cancels each other out, which means c is going to be 4,000. And that means our final velocity equation, so vt is going to be equal to t plus 1/10 of t squared plus 4,000. And we can see that's a bit trickier, a bit of a step up from the previous differentiation questions. You may have also put this, the 1/10, you may have put that as 0.1. That would also be perfectly acceptable as well. Okay, so we've done that. We're just going to get rid of our little timetable on the right. And we're now going to move on to question C. So question C has asked us, what is its velocity when it hits the Earth? And we found out before that hitting the Earth, it was after 45 seconds. So we know that t is going to be equal to 45. So we're going to put t into our velocity equation. So that's going to be 45 plus 1/10 times 45 squared plus 4,000. When you enter that into your calculator, that is going to be 45 plus 202.5 plus 4,000, which is going to be equal to 4,247.5 meters per second. And that would be our velocity as it hits the Earth after 45 seconds. So let's move on to question D. So question D, it's now asking about the displacement, and that's the final part of our equation. So if down the bottom, we had the displacement, that led to the velocity, which led to the acceleration. So we're at the velocity. Again, we need to integrate to get back to the displacement. So the displacement is going to be equal to the integral of the velocity, and that's going to be equal to, we've calculated that down the bottom, the integral of t plus 1/10 of t squared plus 4,000 dt. We can then integrate that. So that's going to be 1 divided by 1 plus 1, t1 plus 1. Then it's going to be plus 1/10 divided by the current power plus 1 plus 4,000 t. And I've run out of room, but I'm just going to put that up the top there, plus our c value. And when we simplify all of that, that is going to get us to 1/2 of t squared plus 1/30 of t cubed plus 4,000 t plus that constant. And that constant is a bit annoying for us. So just like we did for question B, we need to go ahead, we need to find some other information, some other relationship to find out what that C value is. What I'm going to do is I'm going to again get rid of this diagram to create a bit more space. And question D, find the displacement from the point where it first enters the atmosphere. And what it's told us is the displacement would be equal to 0 when time is equal to 0. So that means 0 is going to be equal to 1/2 of 0 squared plus 1/30 of 0 cubed plus 4,000 times 0. And then we're going to add c to that as well. So this, and this, they all cancel each other out, which means c is equal to 0. So therefore, the displacement formula in terms of t is going to be 1/2 of t squared plus 1/30 of t cubed plus 4,000 t. And that there would get us our displacement formula. And finally, the very last question, E, hopefully we have enough room to do it down the bottom. What is the meteor's displacement when it first hits the Earth? And just a reminder, it hit the Earth after 45 seconds. So that means we're looking for the displacement after 45. And we're going to substitute that in. So 1/2 of 45 squared plus 1/30 of 45 cubed plus 4,000 times 45. And when we do all of that maths in our calculator, we're going to get 184,050 meters. And if you rounded that, that's approximately 184 kilometers. So hopefully you found this video useful. What we did is we started using our integration skills to solve problems in relation to kinematics. And the thing I would like to emphasize, when we are finding equations, that was B and D, there is always another bit of information that you need to do to find out what the C value would be. And it may be a hunt getting that information, but hopefully you can find it from the question. Okay, so this is going to wrap up the video. Hopefully you found it useful. Now let's get into heaps of practice.